Okay, 4.2 mean value theorem. The mean value theorem, or MVT, you'll see it written that way sometimes, says if f is continuous, so f has to be continuous on a closed interval and differentiable on the open interval. So as long as it's differentiable everywhere except for the endpoints, then there exists a number c. This number c, right, which is basically just an x value, is a location where the slope of the tangent, which is this, the slope of the tangent, is going to equal the slope of the secant. And the secant is just a line that connects the endpoints, A and B. All right, so if you look down here in the picture, right, here's my tangent. Okay, this line is tangent to this graph, the red part on my paper. I'll outline it on my paper, on my smartboard. Really big piece of paper. So the tangent line right at C is going to have the exact same slope as a line that would connect the endpoints A and B. This is the secant line. And it's not secant like trigonometry. It's just secant. It's a secant line. It's basically the way we would find the old slope algebra. Okay, so now the idea is that if I have endpoints, such as A and B, and if I were to draw a line through those endpoints, getting a secant line, that slope is actually going to exist somewhere else, the exact same slope. And what the mean value theorem does, it guarantees that C, this x value, exists somewhere in the interior of this graph within the parameters of A and B, the interval. Okay, so another thing is having the same slope means that these two lines are parallel, right? Okay, so somewhere the slope of the tangent is equal to the slope of the secant. Now, another way to look at this for the purposes of doing word problems and such, the slope, doing it derivative-wise, is instantaneous. Instantaneous. I can't spell. This is instantaneous, whereas on the other side, it's average. You can think of velocity. That helps. The derivative way is the instantaneous velocity, so the velocity at an instant, whereas the old-fashioned Algebra 1 finding slope way is the average velocity. Okay, so there's a point somewhere where the instant slope is the same as the average slope. All right, so that is the mean value theorem. Okay, so now we're going to look at these pictures. Here I have three figures here. And on figure 1, as you can see, I have endpoints A and B. Now the idea would be that if I were to make a line from A to B, such as that, somewhere on this graph, because it is continuous from A to B, and there aren't any issues like no discontinuities, no sharp turns, no cusps, none of that, it is differentiable. Differentiable, I can't spell today. Because it is continuous and because it is differentiable, then the mean value theorem applies. okay, because these two things happened. So that means that somewhere there is a point where if I were to find the slope of that point, it would be the exact same slope as the slope from A to B. So let's say this was my secant line. I think you can take a pretty good guess. Let's pretend this is parallel, people. So probably somewhere around here, there would be a point where the tangent has a slope the same as the secant slope. Okay, figure 2. Now looking at figure 2, I see that there is a discontinuity. Okay, it is discontinuous. There's a well, you know what? Discontinuous. Let's do that. Discontinuous at x equals 2. See here? That's my problem right there. Now, although it is a closed interval from 0 to 6-ish, it looks, 6.5, it's discontinuous. So, because this graph or function is discontinuous, the MTV does not apply. Oy, can't write today. There you go. All right, next. For figure 3, closed interval, right? From, I don't know if I had to take a guess, -1 to 6.5, 7, something like that. But see right here, I have a sharp little cusp. Because of that cusp, this graph is not going to be differentiable. So it's not differentiable at x equals 2. And because of that reason, the mean value theorem is not going to apply. There will not be a C where the slope of the secant is the same as the slope of the tangent. And that's what it means for the mean value theorem to apply. For the mean value theorem to apply, right? It has to be differentiable, it has to be continuous, and then they guarantee me that somewhere in the graph I will have a slope of the tangent. So somewhere in the graph called C, I will have equal slopes for the tangent and the secant line. All right. Example 1. For f of x equals 5 minus 4 over x, find all values of c in the open interval from 1 to 4 such that f prime of c equals f of 4 minus f of 1 over 4 minus 1. So basically, this is the mean value theorem. They're asking you to find this c that is guaranteed by the mean value theorem. All right, so we need a few things. I'm going to need the slope. So let's just do that real quick. The slope is, so the 5 minus 4x, I can rewrite this as 5 minus 4x to the negative 1 power. So if I derive, 5 is 0, and then negative 4x to the negative 1 power, bring the negative 1 to the front and multiply, so I get positive 4x, and then the negative 1, I subtract another 1, so that's what I end up with. Of course, I can rewrite this as 4 over x squared. So there's my derivative. I'm going to need f of 4. That means I'm going to take the original function and plug in a 4. And when I do, I get 4, 5 minus 1. And then I'm going to take f of 1 and plug that in. And when I plug that in, I get 5 minus 4, which is 1. So this is the stuff I'm going to use in there, into my little mean value theorem formula looking thing. All right, so for this, I'm going to take the derivative. And instead of using x, I'm going to use c, because I'm looking for c. No big deal. If you leave it as x, it's not a big deal. Okay, so 4 over c squared. All right, that's my derivative. I guess I can move that over a little. equals, and then I do good old-fashioned slope, right? So f of 4, we figured out that that was 4 minus f of 1, which is 1, and then 4 minus 1. So you're like, okay, that's the same, sure. So I have 4 over c squared equals 3 over 3, which is basically 1 over 1, right? All right, I'm looking for the c. What is c? I have to solve for c. Best way to do this is cross multiply. Good old-fashioned algebra uno, yes? So I have c squared times 1 is c squared. 4 times 1 is 4. So square root, right? Doo-doo, doo-doo. And I get c equals plus or minus 2. So there are my c values. Now, I'm going to look at my interval. And I'm going to observe the fact that my interval is from 1 to 4. Right? Here's my interval from 1 to 4. Now, the number -2 doesn't exist there. So the c guaranteed to me by the mean value theorem, or in other words, my answer, right, is going to be c equals 2 because it's actually in my interval. And a nice handy-dandy way to write that would be to say 2, a little funky looking e, and then 1, 4. That e means element. You actually learned this in Algebra 1, or you're supposed to. It means element, which means that 2 is actually in 1 to 4. It belongs in there. It's part of it, right? Because it is. I have 1, 2, 3, 4, right? All right. So my answer is 2. And I found it using the mean value theorem because it was guaranteed. There was just 2 of them, but one of them was not in my interval. All right, example 2. Determine whether the mean value theorem can be applied to this function here. They gave us the interval. If yes, then find all values of c on the open interval from -2 to 4 such that the tangent line through c is parallel to the secant line joining the points, -2, -6, and 4, 0. Okay, so this is a lot of words for just basically saying find c as long as this function is both continuous and differentiable. It's a parabola. There's no issues whatsoever when it's just a polynomial function. And this is just a parabola, regular old looking U-shaped function. So it is going to be continuous, and it is going to be differentiable. So I'm just going to jump right into finding c. Okay, so we need the derivative. So this time I'm not going to do all the pieces. I'm just going to go ahead and derive. So 2x minus 1, right? So I'm going to go ahead and write 2c minus 1, and that should equal, and then I'm doing the good old-fashioned slope. So let's see. My, what do you call them? Intervals, my endpoints, right? Here's my interval, or you can use -2, 4, it doesn't matter. They're still the same numbers. I need the y values. Oh, they are so nice because they gave me the y values, right? Here are my y values. Basically, these are my points, right? So I can plug them into the, what do you call it? Oy, the original slope formula. Alright, I'm just going to write some notation there. So let's do -2 minus 4. Those are the, oh, that's going really slow. -2 minus 4, those are the x's. So -6 minus 0. Those are the y's. So my job is to find c. I need to figure out what c equals. So this is staying the same for right now. And then -6 minus 0 is -6. -2 minus 4 is -6. And I have another 1. 2c minus 1 equals 1. Okay, add 1 to both sides. 2c equals 2. Divide both sides by 2, I get c equals 1. So the value of x, which we're calling c, that is guaranteed to me by the mean value theorem, c equals 1, is definitely in my interval, so we're good. Okay, next. Now we're doing 2 stationary patrol cars equipped with radar are 5 miles apart on a highway with a speed limit of 70 miles per hour. So that's the speed limit of the highway. As the truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. The trucker was issued a speeding ticket. Why? Okay, so the numbers can be really deceiving. First off, they gave us information in miles per hour, and then they also gave us information in minutes. So no bueno. So we're going to go ahead and take care of that first. The 4 minutes here, we're going to go ahead and convert that into hours. Let's just keep everything in hours because that's the only thing in minutes. So 4 minutes to hours. Okay, so let's do that. So I have 4 minutes, right? And in an hour, there are 60 minutes. So that's actually 1/15th of an hour. All right, 1/15th of an hour. Okay, so there's my hour. That way I don't have to mess with minutes, hours, crap. Okay, so this is a perfect example of the mean value theorem. It might not seem like it to you, but we're going to go ahead and we're going to assume this is a function and that it's differentiable and continuous, right? And you have to assume sometimes. And I'm going to need f of something equals something, right? And f of something equals something. So my interval, I need an interval. So basically my interval is going to be, and it's going to be time, right? My interval's time here. It's going to be from 0 minutes or hours to the 4 minutes, which is just 1/15th of an hour. So 0 hours to 1/15th of an hour. And that's going to be my interval. And because that's my interval, I'm going to go ahead and plug in 0 and 1/15th, or 1/15, into my function. Oh yes, I don't know what my function is, but I do know how fast they were going. The first time that the truck passed the patrol car, the first patrol car, it says that, let's see here, as the truck passes the first patrol car, its speed is clocked at 55 miles per hour. So at time equals 0, 55 miles per hour. All right. The second time, it was clocked at 50 miles per hour. Okay, so basically what we're doing here is we're looking for what was the average, right? The average speed of this truck. Because whatever the average was, right, according to the mean value theorem, I'm guaranteed to have been able to go that fast at least at another instant. Okay, so let's see. Let's do the time first. It's 1/15 minus 0. And then my y values are 50 minus 55. Alright, so 50 minus 55, that's -5 over, let's see, 1/15 over minus 0 is 1/15. Well, that doesn't look very pretty. So I am dividing a fraction. So dividing fractions, you actually multiply. So this is -5 times 15. So -5 times 15, that's -75 miles per hour. don't be alarmed by the negative. The negative is there because he actually did decrease. And what is that called? The speed did decrease, so that's no big deal. The 75 miles per hour. So according to this, right? And you know what? Let me go ahead. Hold on a second. All right, I rewrote. I went ahead and wrote it all in a column. Okay, so according to this, at some point, right, there was an instant between point A and point B, which is basically the first patrol car to the second patrol car. There was an instant, because this is the instantaneous velocity, right? Let's think of it that way. There was an instant where, although this 75 miles per hour is an average, right? According to the mean value theorem, there was an instant where the truck did reach 75 miles per hour. Since that was the average from point A to point B within those 4 minutes, the truck did actually accelerate up to 75 miles per hour. Okay, so this is the mean value theorem. Although the 55 and the 50 kind of look like he wasn't speeding, since he did it in such little time, he actually, I'm assuming it's a he, did get up to 75 miles per hour. So why did he get a ticket? I'm going to write that down. Hold on a second. All right, so by the mean value theorem, at some point, an instant, between the first patrol car and the second patrol car, during the 4 minutes of travel time, the trucker reached a speed of 75 miles per hour, because that was its average. And according to MTV, at some point, there's an instant where you do actually reach your average. So his average was 75 miles per hour, which means at an instant he actually reached 75 miles per hour, and that is way above the speed limit of 70 miles per hour. Okay, Rolle's theorem is almost the same idea as the mean value theorem, but it was like this theorem was discovered, I guess, by some dude named Rolle who didn't really like calculus. So he made his own theorem, even though it's actually the same thing as the MTV. Almost. It's close. Okay, so Rolle's theorem, let f be continuous on the closed interval from a to b and differentiable on the open interval a to b. So the same parameters, continuous and differentiable, open and closed intervals. But here's where Rolle's theorem differs. For Rolle's theorem to actually work, so basically it's the MVT, but with a special condition. F of A has to equal f of B, which means the endpoints are actually at the same height. So if you look at this picture, here's f of A, here's f of B, okay? So they're actually at the same height. That's the only difference. And because they're at the same height, now my secant line is a horizontal line. If they actually are at the same height, if they equal each other, then there's at least one number c in between a and b, such that the derivative is actually equal to 0. So the reason the derivative equals 0, please remember derivative is slope, right? Slope is 0. Well, the reason why is because if you look at the secant line is horizontal. So if it's horizontal, it's going to have a slope of 0. Okay, so has a slope of 0. And since it has a slope of 0, Rolle's theorem is just guaranteeing that somewhere else between A and B, the graph will have a slope of 0. And in the picture, C is right here, so this would be my tangent. So my tangent line is also horizontal. And actually, if I wanted to, there's like another one down here, right? Okay, and they're parallel, of course. Okay, so let's put that to use. Determine whether Rolle's theorem can be applied f of x equal to f of x equals sine 3x on the closed interval from 0 to pi over 3. If Rolle's theorem can be applied, find all values of c in the open interval. Okay, so if you remember what trig functions look like, we haven't messed with too many graphs yet. But sine, although this is sine 3 times x, which just changes how fat or skinny it is, right? The wavelength, I believe. Sine just looks like this, right? And it just continues on and such. It is continuous, and it's going to be differentiable, so no problems here. So Rolle's theorem can be applied. So now what we're going to do is we're going to find c. This requires a calculator. You can't do this without one. Well, you kind of can, but you have to have the entire circle memorized, or not the entire, but you have to know it. Alright, so we're still going to use a calculator. So f of 0, well actually, before I say that, so this is basically going to work the same way. My derivative has to equal 0. So I'm going to take the function, and I'm going to derive it. So if I derive it, I get, and it's a chain rule, I get 3 cosine 3x. So according to Rolle's theorem, somewhere my derivative is equal to 0. And in the interval from 0 to pi over 3, right? Okay. So I'm going to use c because I'm looking for c, right? Okay, so I'm going to go ahead and we're going to get the c by itself. All right, so divide by 3 to get rid of the 3 in the front, right? And that goes away. So I have cosine of 3c equals 0. Okay, so problem, cosine of 3c. I need to get that c completely and totally by itself, so I got to get rid of the cosine. And the only way to get rid of cosine is to use the inverse cosine. And remember that from pre-calculus or geometry. So this becomes 3c equals the cosine inverse of 0. 0, oh my god, I can't remember words. Anyway, so done there. C still needs to get by itself completely, so divide by 3, divide by 3. So now I have c equals the cosine inverse of 0 divided by 3. Now, what does 0 mean? This is not an angle. Okay, when you use inverses, you don't actually have angles. This is a coordinate. So basically, I'm asking you where on the unit circle does cosine, right, have a coordinate of 0? 0. Okay, so I told you you could use a calculator, right? So let's see. Where is there a coordinate of 0 for x? So up here, the coordinates are 0, 1, and down here, right, the coordinates are 0, -1. Nowhere else is there a coordinate of 0 for x, because that is where x is located. For the top one, this is pi over 2. And for the bottom one, this is 3 pi over 2. So those are the two locations where my coordinate is 0. So c is equal to pi over 2 divided by 3, or 3 pi over 2 divided by 3, right? Because that 3 is still there. All right, so do a little math, right? Pi over 2 divided by 3 is the same as saying pi over 2 times 1 over 3. So work that out, we get pi over 6. 3 pi over 2 is the same thing as saying 3 pi over 2 times 1 over 3. So work that out, and we get 3 pi over 6, which is pi over 2. All right, so those are my C values. All right. Are they in my interval? So I look back on my paper here, right? And my interval is from 0 to pi over 3. Pi over 2, half is definitely bigger than a third. So my one and only answer, right here, pi over 6. Pi over 2 is not inside my interval. All right, now notice all I did was take the derivative, set it equal to 0, and figure out what C was. So this one takes less work. Before starting, I just told you that this is differentiable, no problem. But an easy way to check would have been to just, okay, plug in your endpoint 0. So sine of 3 times 0. Figure out what you get 0. So plug in the other endpoint, which is pi over 3. So sine of 3 times pi over 3, which is basically sine of pi, is 0. So look at that. F of A does equal F of B. Okay, F of 0 equals F of pi over 3. So this would have been definitely good to go for the Rolle's theorem. I just said we were good. All right, next. Antiderivatives. Yeah, you heard me. Antiderivatives. We've been deriving. This is anti-deriving. So it's going backwards. We've kind of done it a little bit before. I guess this is officially me introducing it to you. A function. Look at the big letter, capital letter F. That's there on purpose. A function f of x is an antiderivative of a function small f of x if I take the big F and I derive it, right? And the derivative of it is the little f. Confusing, right? Okay, so the big F is the antiderivative as long as the little f is equal to the derivative of the big F. Makes sense. If I derive f, the big F, and it's the same as the little f, then obviously the big F is the antiderivative. It's what came before. For all x in the domain of f. The process of finding an antiderivative is called antidifferentiation. All right, here we have 3 examples. And basically, well, you know what? Let's go back. When it's just a simple power rule, and that's basically all I started with. I have more, right? But I just start with the simple power rule. With a simple power rule, you're just going to go backwards. So normally we bring the exponent to the front to multiply, and then we subtract 1. So we're going to go totally backwards. Instead of subtracting 1, which is the last step, we're going to add an exponent. And then the first step was to multiply by bringing the exponent to the front. So that's now our last step. But instead of multiplying, I'm going to do the opposite, which is division. And we're going to divide by the new exponent, the exponent I get after I add 1. Now, constants. Constants are tricky because when we derive, a constant goes away. So if I'm anti-deriving, if I'm working backwards, there's always a possibility that there was a constant there. So what we do is we always add a constant. Now I'm not telling you to pick a random number from the abyss and just tack it on to the end of your equation. The way we do it is we just plus the letter C. The letter C does stand for constant. Okay, and that way that will just hold the place for that constant. Okay, here we go. Let me see, where did I put these? No, I think I put them, yeah. Okay, so. All right, we're going to do these 3 first. Find all possible functions f with the given derivative. So what I'm going to do is I'm going to anti-derive all these equations. First one, f prime of x equals 2. Okay, so this means I already took the derivative and I ended up with the 2. Well, the only way that I could end up with the 2, if this is my derivative, means that my original equation was 2 with a variable, right, which is x, of course, 2x. Okay, check it. Derive this. The derivative of 2x is 2. Now, I do have to take into consideration that there could have been a number there that went away when we derived. So there's my constant. Okay, easy enough. When you have a constant, it's just plug in the variable back. Or put it back in. All right, B. The derivative is x. Okay, so right now x is to the 1 power, so I'm going to add an exponent. I add the exponent. And then I have to multiply it by the new exponent. And add my c. There's my derivative. Or my antiderivative, sorry. C. Okay, there is no adding exponents, dividing by exponents here, guys. You have to actually remember, what do I have to take the derivative of to get sine x? And hopefully you're thinking, well, if I take the derivative of cosine x, right? The derivative of cosine x is negative sine x. So this is not quite it either. This is not negative. So maybe my cosine was negative already. And when I derived it, that negative and the other negative canceled out to positive. Plus C. There you go. All right, D. Okay, so let's see. To find my original, power rule is nice and easy. I'm going to add an exponent. So 6x, and then instead of squared, it's now cubed. But then I have to divide by the new exponent. Plus, all right, 4x, add an exponent, so now it's squared. But then I have to divide by the new exponent. And then, OMG, there could have been a constant there. So plus c. And then we would simplify. 6 divided by 3 is 2, x cubed. 4 divided by 2 is 2x squared, plus c. And this would have been my original function. All right, E, same idea. Let's see, 10x to the 5th, but then I have to divide by 5, minus 2x now to the cubed power, but then divide by the cube, so the 3, plus, okay, x has an exponent of 1, so I'm going to add 1, but then I have to divide by that 1. And then, ooh, 3, that's a constant. So if I derived already and I ended up with just 3, that means that there was an x with it, right? And then, of course, there could have been another constant. And there you go. This one can be simplified a little bit. 10 over 5 is 2. But that's it. Everything else is going to stay exactly how it is. All right. F. Ooh, negative cosecant squared x. Does this look familiar? Let's see. When I have the function cotangent of x, right? And I have to derive that. Let's see, if I derive cotangent, I get negative cosecant squared x, don't I? So, negative cosecant squared x, the original function was cotangent. You have to be able to recognize this. Plus c, because there could have been a number there. All right, I'm done. Please do your homework, which was not a lot, I think.